In this video, we are going to finish the proof of the theorem that we started last time, which is that if x is in a principal ideal domain R and x is non-zero, then there exists a unit U and some irreducibles P1 through Pm, possibly none of them if x is a unit itself, such that x can be written as a product of that unit and those irreducibles. In other words, x is factorable into irreducibles, perhaps none of them if x is a unit. Last time we got started, but we ran into an obstacle. We only managed to prove that x has an irreducible factor. And in fact, we proved that not just for the x named in the theorem statement, but really the argument that we used would have worked for any element that's non-zero and not a unit. Certainly a unit will not have an irreducible factor, but anything else will. If x is irreducible itself, then that's the irreducible factor. And if x is a non-zero, non-unit, and non-irreducible, then we can write it as a product of two things, neither of which is a unit, and then use the ascending chain condition to show that eventually we get an irreducible, even if it takes a few steps. All right, so really what we proved that if y belongs to R and y is non-zero and non-unit, then there is some p, some irreducible p, and some y prime in R, such that y equals p y prime. And that y prime could be a unit, but in any case, this y will have an irreducible factor. So we're going to use that to complete the proof of this theorem now. So let's assume R is a PID, hence Noetherian via previous theorem. And X belongs to R and is non-zero. That's all we're going to assume. Now, if x is a unit, we're going to start the same way we did last time. If x is a unit, then pick u, the unit in our factorization, to be x, and m equals 0. So then we just have x equals u, and we are done. In this case, the list of irreducibles is empty. Easiest part of this proof. So what about the other case? If x is a non-unit, well, here's the game plan. We're going to start with x, and again we'll call that x naught. That's our starting point. This time, because I've proven that every non-zero non-unit has an irreducible factor, I can peel one off. I'll call that P1, and then the other factor will be x1. Now it's possible here that x1 is a unit. If x1 is a unit, then that's going to be my u, and P1 is going to be my irreducible. If x1 is a non-unit, then I just make an observation. The observation is the ideal generated by this is a strict subset of the ideal generated by this. And now we start building that chain again. Okay, now if x1 is a non-unit and I'm not done, then well, it's non-zero and a non-unit, therefore must have an irreducible factor, P2. And then the other factor will be x2. Again, maybe x2 is a unit. If so, let that be u. And then I've got u times P1 times P2 equals x. If x2 is not a unit, then we repeat the argument. And we keep going, and by doing this, we are going to build a chain of ideals that is strictly ascending. And we know that that can't happen. Eventually that will have to stop. So that's the game plan. In fact, pretty much what I said is the proof. We are going to take the care to write it down, but there's not going to be much in the way of new ideas beyond what I've already written. All right, so if x is a non-unit, let x naught equal to x. Because x naught is a non-unit. It has an irreducible factor p1. So x naught equals p1 x1 for some x1 in R. If x1 is a unit, then pick u to equal x1. And then we have x equals u times p1, and we are done. Okay, now at this point I'm going to try and just describe what would happen at every stage of this construction, not just the x1 stage. Okay, so at this point, if we've just constructed xj, and xj is a unit, then pick u to equal xj, that's a u, and we have x equals that unit times all the irreducibles I previously selected, u, p1, p2, etc., up to pj, and we are done. That's great. If xj is a non-unit, well then, we know xj has an irreducible factor, which we will call p sub j plus 1. So xj is equal to pj plus 1, xj plus 1, for some xj plus 1 belonging to R. Okay, so that's the next stage of this construction over here. I'm splitting that xj into a pj plus 1 and an xj plus 1. Okay, and that's how I describe the construction. So I'm just going to say we perform this construction repeatedly until we encounter an xj, and in fact I'll just call this xn, that is a unit. At this point, we take u, our unit, to equal xn, and have x equals u times p1, p2, all the way up through, I believe, if we have xn, then we've just constructed pn, and are done, because that's a factorization into a unit times irreducibles. Okay, that's if the construction eventually stops. What if it doesn't stop? If this construction never stops, then we have the following. We have an ascending chain of ideals, x naught, strict subset of x1, strict subset of x2, strict subset of, well, you get the rest. This is an infinite ascending chain of ideals, strictly ascending, which is impossible since R is Noetherian. So this means the construction must stop at some point. Therefore, x is expressible in the form x equals unit times irreducibles. And that's the proof. Okay, But let's take a closer look at one thing, because I want to make sure that the reasoning we used in the last video still holds up here. So why is it that the ideal generated by xj is a strict subset of the ideal generated by xj plus 1? Is that still true, even though we're using slightly different assumptions here? And the answer is yeah, we just need to take stock of the ideas that we used in proving that last time. We know that xj is equal to pj plus 1 times xj plus 1. Okay, so at least we know xj belongs to this next ideal, and thus the ideal generated by xj is a subset. Okay, but why is it a proper subideal? Well, if xj plus 1 belonged to the ideal generated by xj, then we'd have xj plus 1 equals xj times something else. And I'm trying to make sure we don't reuse a symbol. I think we can use q here, times some q. Okay, but then we can do the same thing that we did before, where we say xj is equal to pj plus 1, xj plus 1, and then substitute for xj plus 1 this product, pj plus 1, xj, q. And then from there we end up getting, again using cancellation, that 1 equals pj plus 1 times q, which means this is a unit, and that contradicts the fact that we said it's irreducible. And that's where we get the fact that each ideal in the chain is a proper subset of the next one, is because we can run this entire argument again. There's really nothing new about it. The only thing that is a little bit different is this time, rather than just saying this is a non-unit, we're saying this is irreducible, which makes it a non-unit. So anyway, okay, we should celebrate this. This is a terrific proof. So what we have now proven, in the last video we proved that every non-zero non-unit in a PID has an irreducible factor. That was important, but now we know even more. We know that every non-zero element of a PID factors into a unit times irreducibles. Yay! And in fact, actually, a lot of the time when you see this theorem stated, they will de-emphasize this part, the unit, because really, one thing that you can say, if you have a non-zero number of irreducibles in your factorization, you could just wrap this unit into one of them. I left it separate in our factorization because it was kind of nice to have here as a way of discarding that last x sub j. But really, you could state the theorem as every non-zero element is either a unit itself or it factors as a product of irreducibles without needing that extra little unit factor. But I kind of like the way that this one worked out.